Hi everyone, and welcome to a new interview. Today I'm talking to Pradeep Niroula about a quantum algorithm designed to help with string pattern matching. We're going to be talking about the conceptuals around that sort of methodology, but then also the physical implementation details associated with something like this. I hope you enjoy our discussion. Pradeep, thanks for joining today.
Of course, this absolute delight on my part.
I figured in order for us to just get settled on the topic that we're going to be talking about, which is string matching and the algorithm that you've put together for string matching, would you mind introducing just what that is very briefly?
So the string matching problem is very common. It's a very well-known problem. Given a very long corpus, a long string, or could be an image, you're trying to find a pattern, an exact pattern that fits in the string, or inexact ones with like a few mistakes. And you want to do it as fast as possible. Every time you search a document, you're doing pattern matching. And the uses have expanded given that today there's a lot of visual information out there. You're querying images, and the need for pattern matching has increased drastically. And the one-dimensional version of a pattern matching problem is the string matching problem. Yeah, the problem has been around for centuries, and we have a lot of extremely good algorithms to do it. And what we propose in this paper is a quantum version. We provide an exact implementation of what the quantum version of the algorithm looks like, and we compute the complexity and the speed ups we get. And when we published, this was as good as it could do on a quantum machine. And yeah, in short, the paper is a quantum implementation of a string matching algorithm.
Awesome. If we think about the industry as a whole, obviously, as you said, we have many applications of string matching, not necessarily just string matching, but pattern matching in general. And if you have a more efficient algorithm, of course, you're going to have just efficiency gains in a lot of the applications where this occurs. Are there also currently applications of this where the time complexity is so critical that you would potentially unlock new ways of, new functionalities, if you will, or sort of applications that are pivotal on us actually becoming more efficient in our string matching or pattern matching procedures?
Right. So for instance, searching a Word document for a word may not be a very complex problem. But if you're searching for like a particular protein sequence in like a very long protein sequence, then the problem starts becoming more complex in execution and also important in its value to the society. Another extreme of this is trying to find patterns in huge scientific data sets. For instance, if you follow the news about gravitational waves, the amount of data these experiments produce is massive. They fill a lot of hard drives with data, and the data processing job in these experiments often simply looks like trying to find the right pattern, trying to find the right signal in a huge data set. So in those extreme cases, string matching alone could be the potential limiting factor right now, and speed ups on that method could certainly help. Bioinformatics, like scientific data processing, things like that.
Mm-hmm. Understood. If we compare the algorithm that you've now developed to what I believe was the state of the art before this, so the Knut-Pratt-Morris algorithm,
Right.
what is sort of the difference in performance between those two? If we just summarize the key
So
takeaways.
that's right. That's a very important question. So the KMP algorithm has been around since, I believe, the 60s or the 70s at the latest. And it's a classical algorithm, meaning you can run it on your laptop, and it was built to be a classical algorithm. And its complexity is linear. What I mean by that is if you double the size of the document you're searching, the cost of the time cost of searching the doubled space increases, like it almost doubles. So the quantum version of this offers a quadratic speedup, and this has been known for some time. What I mean by quadratic is that when you double the almost the time complexity of searching a document of size n doesn't increase, it doesn't scale with n, but rather with square root n. So if you increase the search space by 4, you only increase the search time by 2, 10, so 100 to 10, something like that, by a factor of square root n. And that's kind of a generic speedup that quantum algorithms provide. You might have heard of Grover's algorithm, the very famous version of this, where you're searching through a database of n items, and you can do it in square root time. It's like one of the milestones algorithm on quantum computation, and we use a lot of their techniques as well. But again, like just so we're absolutely clear here, we're not competing directly against KMP. These things operate. KMP is one of the best classical algorithm. What we did was, like when we wrote this paper, there were like proposals of doing string matching using quantum computer, but what a lot of this work didn't describe was like an exact implementation of it. If you were to give me a quantum computer, how would I actually exactly do it? And you could use a quantum algorithm just to replace the classical algorithm. Just feed like a big string on a quantum computer and search it. But often you want a quantum algorithm to be a part of another quantum algorithm, for instance, a factorization problem, or to solve other challenging problems. In this particular instance, I think that it's important to stress that the speed up we get from classical linear complexity to quantum quadratic complexity, and that's important, but it's not as dramatic as the speed up you get in factorization, where you go from exponential complexity to something in a polynomial. That's way more drastic, and again, So we certainly, if you had a quantum machine, we could run this algorithm by itself, or we could use it as a subroutine of some other algorithm.
Mm-hmm. Okay. You say that it's not directly competing with the KMP algorithm, and is the reason for saying so you said that you technically could implement it in the same way as a classical algorithm and simply use it for string search, or that you could make it part of a larger quantum computation and use it as a part of that. So I acknowledge that the algorithm that you're proposing now is more versatile in a way and covers some use cases that the KMP algorithm would not necessarily do in the same way, at least. Is the reason...
Sorry, let me add a bit more color to that.
Okay.
I mean, you could of course directly implement KMP on a quantum computer, but you wouldn't get the speed up. To see the speed up on a quantum computer, you want something that looks like what we proposed. And when I say we're not competing with KMP, you can't just take a laptop or an Apple chip and use our algorithm. That's going to be useless right now, where we need specialized hardware to get to the same stage where we are benchmarking against state-of-the-art techniques.
Yes, absolutely. What I want to get to with the question is, if we think ahead for where this kind of algorithm might be the most competitive, do you see it as a potential replacement, or these kinds of techniques, to the classical algorithms for string search in general? Not, of course, on a personal computer, but I'm talking for large scale, let's say, industry applications or research applications where you might have access to this kind of infrastructure. Or do you see the utility of this applying to a completely different setting? Not sort of traditional string searches, but perhaps string searches that arise as part of a quantum computation specifically.
That's an open question. I have no idea, and a lot of that would depend upon uh, just how good of a machines we can build, right? So, like I said, the complexity improvement from linear to quadratic, this only becomes it only manifests in a significant way on your clock time only when the data set sizes are extremely large. Uh, and the question ultimately becomes, okay, will we get to a stage where we see this crossover between classical time and quantum time happening? And that, like, I have no idea. I wish I knew. I can, again, if the machines become good enough, I can see it totally being used as like a complete replacement for a classical like KMPs or the algorithm. Uh, but again, the scale where we have to operate to achieve that is rather massive, and it's like unclear to like anyone right now how quickly we get there and how if we'll get there at all.
Is it clear what the scale would roughly need to be before this would realistically start having an advantage?
Like I would imagine like petabyte terabyte size data sets would be, and again, I mean, we have use cases like that, like with scientific and like data matching, and I would hope, just given the scale at which like data keeps on increasing in the world, uh, reaching that scale probably will not be a problem. The real problem is just if we will build a quantum computer to accommodate a problem of that magnitude, and yeah.
Okay, so let's transition to looking at the actual algorithm. So I'm sharing on my screen now the five sort of high level steps associated with the algorithm here. And if we start with maybe just the preparation of this and how we get to, well, prepare the problem for actual manipulation. You mentioned that you would initialize two quantum registers, and if we maybe start there with how you would actually do that in practice. So you have these bits corresponding to the text itself on the left-hand side and then the pattern that you want to match with. If we talk about the hardware aspect of this, how do you actually initialize two registers like that? Could you maybe shed some light on what that process is like?
So so you have a quantum computer and it has qubits in it, right? So what I can just say is the first, uh, like if it's on a chain, I can just partition it into two groups. My qubits on the left, they represent the data, and qubits on the right, they represent my pattern. And depending on the architecture, qubits are kind of abstract objects. You may be using photons to implement them. May be using a superconducting transmon to implement them. But somehow, yeah, you would have to partition the qubits into like two sets, the same way you partition classical memory, like RAM, and yeah, that's doable. And to initialize, what I mean is like the same way you set a classical transistor to one, a classical memory to one, we can simply rotate a qubit from 0 to 1. And that would encode the binary representation of the string and the pattern you're trying to search. And once you have the qubit, all you need to do, and all qubits come with these rotation operators, you can just flip a bit, and that's your initial state.
Would it always be such that you have one qubit associated with each bit of the string? So you have a bit representation of the string. Is that always one-to-one comparable to a qubit in any of these like architectural implementations?
Yeah. So a qubit is designed as a unit that can represent superposition of 0 and 1. You could go to a different atom, a different architecture, where you're not using qubit but qubits or q4 bits, in which case, like, each qubit can represent four different information levels: 0, 1, 2, 3, or 0, 0, 0, 1, 1, 0, 1, 1. But again, the current paradigm is that we're building qubits, and in that paradigm, 0 and 1 would be what you would represent. But again, if we can find better architectures in the future, like you could represent however many information in a single unit.
Okay. So maybe then moving over to step number 2, and I guess this is where we actually start manipulating this in the context of, doing something with this information. So you say that the first thing you do is you incur superposition of these end states for the string. And if we start there, you can immediately see some resemblance to the Grover's algorithm that you mentioned before. One question I would have before we actually go into the details of how you do this is the general idea that you had when you developed the algorithm that you wanted to leverage Grover's algorithm and that you're, for that reason, superimposing them as the first state? Or is there another rationale for how you approach developing the algorithm to begin with?
So I mean, we didn't. Again, Grover's technique is a generic technique. You can use it's like a sword. It's like a bubble sword. You can use it wherever you can. So yeah, I mean, one just finding this superposition was a natural thing to do because quantum computers aren't powerful without elements like superpositions and entanglements. So you need to get there at some point. And once you have that, like Grover's gives a natural way of finding the right match.
Okay. And then additionally, you do this bit shift operation, which you have a specific quantum gate for, and we can get into that in a second. Would you mind describing why, like, what is the rationale for putting that in place on the string?
So, so basically, we want to turn the matching problem into like a nice search problem. And the way we do this is saying, okay, I have a string like this, and I have a pattern here. I can only run comparisons between. So in a quantum computer, we often struggle with conditional statements. We have to predefine the quantum circuit ahead of time. So if I fix the positions of my pattern and the position of my the string I'm searching, every time I compare the two, I can only compare them at like a particular position and not through the whole thing. Mm-hmm. So what I would like to do in this case is create a superposition where my string is just rotated one bit at a time. And when I have superposition at that, I have the string like almost completely rotated, like shifted by 1, 2, 3, 4, 5. And now when I do a comparison between the string and the pattern, I'm comparing all of them, all of those possible rotations or cyclic shifts, as we call them, at the same time. And that will let me identify which bit matches without much complication. Just makes things much simpler. Once you have a superposition, you can do the compare against the entire thing using a single step.
Mm-hmm. Okay. And before we get into that particular operation, a lot of these things, do they already exist in a standardized form? I'm thinking this kind of shift operation for a string, it's something that to me seems like there would be a lot of, I don't know if open source would be the right word for it, but nevertheless that the scientific community would have, let's say, sets of these operations that you sort of have solved a priori and that you can leverage. Is there anything like that for these kinds of problems?
So when we did this, actually, we were not aware of anything like that, and we did some search on the literature, and we had to come up with what would be a good way of like a fast, efficient way of doing the shifts. And we actually detail like that step, like doing that construction is also like a chunk of the paper. Later, like maybe like a year or so later, we did find like other works kind of repeating similar ideas in other domains like chemistry. So it would be nice to have like open source set of techniques, but again, just given the maturity of the field, we don't have that. Like for instance, even simple problems, like if I have two numbers in qubits, how do I multiply them? Or how do I divide them? You will think all those primitives are kind of well understood and very, straightforwardly obtainable, but it's not quite so. It's like even basic operations like that, like need you to like try hard and often come up with your own method that fits your purpose.
Why would you say it's like that? Is that due to the fact that the different circuitries that you would build become like require unique solutions for it necessarily, or is the problem more about actually finding someone who did this in a reliable way and that the landscape is very hard to dissect?
Uh, I think the landscape it's just a very limited set of people and who are looking into this, and uh, and the literature is just not good enough. Maybe in like 5 years, 10 years, like we'll have everything uh, like ready and open sourced, uh, but the literature just is like kind of small for you to have all these like problems done. I mean, like look, I mean there are like the fraction of people who design quantum algorithms to the fraction of people who use classical algorithms is like minuscule,
Mm-hmm.
and and yeah, like I mean, some people, and there is like an active effort trying to compile a list of like all possible quantum algorithms you could use, and there's a website, Quantum Algorithms Zoo, if you've heard of it, where people have tried to enumerate everything that exists in the literature, but again, like unfortunately, just given the maturity of the field, it does not exist. And other
Mm-hmm.
important aspect of this is like until like a few years ago, quantum computers were nowhere close enough, good enough for us to even contemplate of these ideas, right? Like if you went to someone 10 years ago and said, "Oh, I want to add 10 like bits on a quantum computer," that would be an insane proposition, like very, very
Mm-hmm.
far ahead of the time. And it's only like very recently, just like last 10 years or so, like people have even started thinking about, oh, how do we add on a quantum computer? How do we do the shifts on a quantum computer? And I think that's the reason why like it's kind of sparse, the resources you have available.
Mm-hmm. Just in general, when you try to dig out research, so acknowledging that the field is very sparse in terms of publications, how do you generally dissect that? Is it like whenever you would go looking for some kind of result like this, not necessarily restricting this to quantum algorithms now, but just in general when it comes to dissecting a research space where you're very deeply involved, let's say, what is the process for that? Do you usually leverage these kinds of third party websites like you were talking about before that would try to enumerate different, like, try and paint the entire landscape in some way? Or is it more that you need to constantly keep up to date with the latest research being published yourself and try to keep that sort of in the back of your mind?
Right, right. Uh, it's not that difficult, but it's also not so easy. And the easy thing to do is to go to someone who's been studying this for some time and just ask them what exists. And sometimes they know the answer if they are the expert on the subject. Other times we're just doing citation search, like when you go to Google Scholar or Google and see what's the paper that comes closest to what I'm trying to do, and you get a list of all the papers that cite those papers and all the list of papers that cite the other papers. And if you following this citations chain a couple of levels down, usually covers the entire space of the relevant subject matter. So yeah, so even if you're not, it'll be ideally you would like to keep up with what's coming out every year, but often that's difficult just given the volume of research being produced every day. So we often just simply go by citations. You go to a conference and see what was the latest work, and if it seems even close to what you're doing, you can ask the researcher if they know of any prior work that's more relevant to you.
Mhm. Okay, good. So bringing this back maybe to the algorithm again, we're at step 3 now. So this is where you actually compute XOR between the first m bits of the first register and all m bits of the second register. So this is in my mind, the actual comparison now. We've shifted the qubits. Now we perform this XOR operation that gives us some way of dissecting or some way of telling whether or not we actually have a match. Can you explain why applying an XOR operation like this actually gives us a result in the second register that's useful?
So, basically, right now we have a superposition of all the states in all its like shifted form, right? So basically, it's a document where everything is shifted by one. And you're looking at, okay, does the first k bits of this string sort of matches the k bits of my pattern? And that's the comparison. You're only allowed to compare the first k bits of the registers. And once you do the comparison, you need to be able to, and again, like this is a quantum computer. We don't have a division between a CPU and a memory. The CPU is the memory right now. So you need to be able to store somewhere, or record somehow, if like a particular element in the superposition is a match. And what does XOR do? Like the XOR of two strings is zero if the two strings are complete matches. Otherwise, the XOR value is not zero. And based on whether the string is so basically want to record the XOR value in our pattern, so that in the next step we can check, is this XOR all zero? And if so, let's filter this element. So you need to do XOR to just see if it's a perfect match, or if it's like if one bit is unmatched, or maybe a couple of bits are unmatched. And XOR is the operation that lets you compare binary strings and see a match.
Mm-hmm. Mm-hmm. A very naive question, perhaps, but when we conduct this XOR operation, are we doing it for one shift? I believe the value that you use to indicate that is k. So for one k value, or in the algorithm, are these being done in parallel due to the fact that we have a superposition in place?
So there are two relevant numbers. So the first number is the size of your string, right? And that's n. And there is the size of the pattern, which is k. So and for each bit in a pattern, I want to compare against its corresponding a bit in the string. And so I have like k comparisons to make for each bit in the pattern. But these bits are independent. Like the comparison of one set, zeroth set, tells you nothing about the comparison of like the one set. They're like completely independent, so you can run them parallelly. So you're doing k XOR comparisons as a single step, and hardwares allow you to do that. So it's k comparisons, but effectively that amounts to a single time step.
Okay, good. So then what we get in the final register is, assuming we're not doing a fuzzy search, something where we either have a complete, let's say, serialization of this second register, which would correspond to a match, or not, which would not correspond to a match. You then mention in step 4 and 5 that you conduct, a generalized Grover search with amplitude amplification to identify the state where you have this match. We can get back perhaps to the fuzzy search in a second, because I guess that would be the more sort of involved one that we need to discuss. But for the one where we don't actually use a fuzzy search, what is the need for having this step? If we already now conduct this XOR or apply this XOR operation and we get a totally serialized state, don't we already know that we have a match? Why would we need to apply steps 4 and 5?
No, you do not. So this is extremely important, and this is where I guess a lot of confusion about quantum comes from. So right now you have a superposition of all possible strings and their respective XOR match. If you and again, like you don't see them; they exist, but unlike a classical computer, you can't read them directly. Right, so if you go and measure like a quantum computer at this stage, you're going to get any of these XOR patterns, any of these like n-shifted strings randomly. So, and what we want to do is to only pick out, like instead of getting measurements randomly, we want to increase the probability of getting the result with where the XOR matches 0. Like, and increasing this, and that's called amplitude amplification. Without amplitude amplification, this would not work, because what you're getting after superposition is a completely random value from the set of elements in superposition. So an amplitude amplification will let you only pick out the things you care about, in which case where the XOR values are all 0. And so just because things exist in superposition doesn't mean that you as a user knows what the right answer is. And for you to know, you need to amplify the amplitude and do the measurement and hope that the answer is correct, and it's correct with a very high probability.
Okay, so to formulate that in another way, and correct me then if I'm mistaken here, but you have a wave function now that's spread out across the different states. One of those states corresponds to the one that we actually want, and that we can, where this vector or this register would be zeroized. And what the amplitude amplification stage does is it takes this wave function and converges the probability to the one state.
Exactly. It's like a very spread out wave function. It converges to a hopefully like almost a Dirac distribution, or a very peaked Gaussian.
And if we extend that concept slightly now, so I guess that's somewhat clear if you're doing an exact match. If you were doing a fuzzy match, how would you be able to extend this slightly to also incorporate that? Because then your second register would not be zeroized. Could you just explain that?
Right. So the number of zeros on your second match is the reflection of how many bits actually match, right? So if you want to say do a fuzzy match where you are you let one mistake, one bit to be unmatched, you just want to make sure that the XOR data you have has only one in like any position. And that's where like addition, and that's when you need addition circuits. Now you want to be able to add up all the ones in your XOR string and see if that value is less than your fuzzy match threshold, and then do the amplification. And that again, this process of like adding up bits and doing an arithmetic, less than check, that's, you would think it's trivial, but like it really is not. It's like, I think it's more involved, and we believe the general idea remains unchanged as long as you figure that part out. Again, it's not extremely easy, but it's also not a blocker. You can do it, and So basically, you would add up the number of bits in your XOR results and see how many unmatches there are.
Okay. Maybe if we speak about this conceptually and we just have a look at the Grover oracle here, I guess this is how we would rationalize it without going into the details of what the actual implementation of this would be like. So could you maybe explain what a Grover oracle is, without going into too much detail into generalized Grover search, but nevertheless just to paint a broad picture of what this kind of function that we're looking at here is, and why this function in particular that we're looking at now would help for amplitude amplification if we're considering the fuzzy case.
Right. So Grover oracle. So when you have a superposition, a Grover oracle tells you which elements the superposition matches your search criteria. So right now we have computed the XORs. We hope there are some XOR data with all zeros, suggesting a complete match. But the quantum computer does not know that they exist, and you want a Grover oracle to go through all these things and just like check if something is all zero. And And what it does, like to be a bit more technical, is that a Grover oracle, whenever superposition, say like 0 plus 1 plus 2 plus 3 plus 4, it picks out a state, say 2, and adds a phase to it. So it makes it like -2, 0 plus 1, -2, 3, 4. Again, this all exists in superposition, so you don't really get to see any of it. But like being able to mark using a different phase uniquely the things you want to search for, it allows Grover search to iteratively converge the probability distribution towards those values.
Okay, great. Then I think we covered the conceptuals of the algorithm. Maybe we can go back now to this shifting of the original string, because you have an explanation of that also here in the paper. And if we maybe start talking about this circuit diagram here for the circular bitwise rotation operator, would you mind describing just what this illustrates? What's the idea for how you constructed this operator that would shift your string?
Yeah. So what's happening here is that so I have a string of like n bits, and I want to turn that into a superposition where each state is shifted by like a number, right?
Mm-hmm.
And I want to do that in a single operation, And one way of doing this, I'm sure there are many, is that I make another very small register that is a uniform superposition of 0, 1, 2, 3, 4, 5, 6, 7, 8 to n. And that's easy. That's easy because we can start with a quantum computer in all 0, and you apply a Hadamard gate and that on all qubits, and that turns it into a uniform superposition of all numbers. And now what I say is, okay, so I have a string and I have a all numbers in superposition. Now I can just apply an operation that looks at the number in a superposition and rotates the string by the corresponding value. So here in this in the figure 1, right? So I have the K0, K1, K2, Kn-1 representing what I call as index values, and my string is encoded in T0 to T capital N-1, and I want to rotate the string based on my data in the index value. And one way of doing that is saying, okay, let's look at the first bit, and if the first bit is 1, we move the whole thing by n-half, like, right? If the second bit is 1, we move it by n quarters. If the third bit is n, we move it by n-eighth, and so on. And that way you can generate the entire superposition. So you need this additional overhead to even tell the quantum computer how much to rotate, the string you're searching in.
Mm-hmm. Okay. If we then move over to figure 2 as well, this is the diagrammatic representation of the circular shift operator. And this one is
right.
A representation of each of these, is it? Or what does this figure represent, if you were to explain this one?
So, like figure 2 is simply figure 1 in action. If I had 8 things in my 8 things in my string, how would I, for instance, give me a second. Yeah, how would I, for instance, shift each by 6? And the way I would do that is first move everything by 2 and then everything by 4.
And if we think about that from an implementation point of view, what would that actually correspond to, let's say, in a quantum computer?
It would
How would you, Yeah, can you please draw a parallel between this conceptual image and then what the hardware would be doing when you actually apply something like this?
So all it would be is a swap operation. A swap operation simply takes two things and switches their position, and that's relatively easy to do. And so basically, you would pick out the position you're trying to swap and you target and implement this gate, and you swap it. Yeah, and that's like a natural operation for a quantum computer.
Mm-hmm. Okay, so in conclusion then, for this rotation operation, what you really need is a set of swap operators applied in a sophisticated way. The essence of it comes down to that, with additional logic for understanding, or let's say how you need to swap these bits.
Exactly. So, I mean, the focus here really is to unit swap operations. The idea is simply to arrange them in such a way that you can do a lot of them parallelly. And and that's relatively straightforward. And so once you have swap operations, like you said, a clever design on how to the order of execution, and you get there.
Okay, good. So if we start zooming out a little bit again, talking about the algorithm in general, you mentioned in the paper that the algorithm fails with a probability 1/n. Can you explain why that is? Why is it that this algorithm sometimes fails in the matching procedure?
So, Grover's algorithm is probabilistic, and probabilistic meaning that you are never guaranteed a solution with probability 1. You may be able to get to 99% or some value, but there'll always be some uncertainty. Especially so right now, if you keep doing this Grover search for a long time, you get almost perfect solution. But again, we don't want to incur too much cost. We want to do it in square root n steps, and that's critical because otherwise we won't have a quantum advantage. And when you run it for that time, for that number of steps, it turns out the error roughly corresponds to 1/n. And but again, that's not a problem because all that means is you have to run the algorithm 2 times to get a correct answer, because every time you run it, the probability of failure like multiplies, right? So running algorithm twice, incurring a constant overhead is not that big of a deal.
If we focus on gate complexity for a second as well, so that's something you also mentioned in the later parts of the paper. Can you briefly talk about the gate complexity of this algorithm, whether that's a significant concern or not?
So gate complexity is a count of the elementary operations you need to do to run an algorithm. And each gate incurs, cost and time and energy and everything for the quantum computer, so you want to minimize it as much as possible. So and there was a time when we couldn't do more than one gate at a time. And what that meant was the time complexity would be the same as the gate complexity. But now I think we're entering a paradigm where we can parallelize all these gates. And it turns out, like if you can parallelize a lot of operations and run them at the same time, the gate complexity remains the same, but the time complexity can be reduced dramatically. So if you just look at the gate complexity, I believe it's still linear in n, but when you just because of the clever arrangement of swaps, the overall time complexity is reduced, and often for execution, the time becomes like a more meaningful thing for an end user than the actual number of operations that's happening. And we don't care how many operations the computer is doing underneath, as long as the wall time is reasonably small. And for us, we're trying to optimize for time and not the gate. I'm sure there are other algorithms. Maybe there are other versions where the gate complexity is reduced at the cost of time complexity. But we don't want to go that route.
Mm-hmm. The one consideration I had was whether the gate complexity is related to the fidelity as well. If you're thinking about a concrete implementation of this. Would it be
Absolutely.
feasible? So it is related, right? In the sense that a poor gate complexity, let's say, would lead to, in practice, an algorithm that's hard to implement on an actual system without incurring too much losses.
Right. Right. So absolutely, for near-term machines, the fidelity increases geometrically in the number of gates, and therefore you can't run too many gates. But all these things, I think they become more meaningful in a fault-tolerant regime, where because of error correction, we are guaranteed to have almost perfect execution for an indefinitely long time. And in that regime, fidelity is not really a concern because error correction guarantees you the perfect, almost perfect execution, and the gate count isn't really a priority in that regime. So yes, so if you care about near-term execution, gate is probably the more relevant factor, but I think it's more relevant in the fault-tolerant conditions.
Great. When it comes to the algorithm, there's really only one more question I have, which is a mentioning that you have in the paper where you say that the technique can be extended to solve pattern matching problems in higher dimensions as well. Are you able to explain sort of conceptually how that would be possible, or is that too technical perhaps?
No, it's rather simple. So right now we have uh, like a chain representing a string. So basically, we would have like a grid representing pictures, and the same way as we shifted shifted each string by a certain number, you can shift like all the pixels vertically and horizontally at the same time using the exact constructions figure 2 1 and 2, just in two different directions. And and again, like the XOR matching is fundamentally the same. Now you have a superposition where all the pictures are shifted by bits horizontally vertically. You do an XOR in one corner, and you get like a set of all zeros if there's a perfect match, and then you use the Grover oracle to see if it's a zero, and then into Grover amplification, and there you get the answer. So yeah, so the ability to cyclically rotate, it's independent of the number of dimensions. You can always rotate in more and more dimensions if needed, and everything else stays the same. As I guess this case.
Okay. Just zooming out, a final question on sort of research applications in the space. You mentioned before that the amount of research being conducted isn't nearly comparable to what's being done, for example, in the classical case. What do you think would be needed for the space of developing quantum algorithms in particular to gain more traction, and for these kinds of problems to, just have more researchers actually focus on them?
Right. Like invention comes from need, right? And before, like I said, like until a few years ago, people weren't even thinking about this. Now, like we're at a stage where we have like small quantum computers, but they're all noisy. So we even don't have much attention being devoted to fault-tolerant versions of this, like testing whether these algorithms can sustain the overhead necessary for error correction and detection. So it would be nice to have like a version of all these algorithms developed, thinking ahead in the future, like 10, 20 years down the line. That would be extremely useful. And there are people that, like continuing this work. There are papers on string matching, a relevant work like written every few months or so. There is kind of work being done, but it'd be nice to have it a bit more forward thinking. Yeah.
Okay, good. With that, Pradeep, I think we can cut the interview here, actually. Thank you very much for taking the time to describe it. I appreciate you doing so, and I hope you have a great rest of your day.
Of course. Thank you so much. This has been an absolute delight on my part. Yeah.